Hello everyone. In this video, I'll be talking about sections 2.6 and 2.7. So these two sections are actually not going to appear on any quiz or exam, but you do have homework regarding these sections. So FYI. Inequalities, solve compound inequalities, that's 2.6. So I'm gonna fly through some of this and just introduce the concepts like through actual example. So going down to this first one, we have this symbol. So this means less than. So it would be true to say that 1 is less than 2. In other words, it would be false to say 1 is less than 0, right? That's actually not true. So I could kind of slash that out that way. So this is true, 1 is less than 2. It's not true that 1 is less than 1, right? Less than means strictly below. So when we have inequalities, we're no longer looking for when there's exact equality, right? So this statement just means when is this thing less than this thing? Okay, so for what ends does this thing on the left produce smaller outputs than this thing on the right? So your addition property of equality extends into inequalities. So what I'm going to do is actually add this 6 over just like it was an equation. So I'll say 3n, now just less than 7n plus 10. So I'll continue and just kind of get these like terms together. So subtract 7n. That would lead to negative 4n less than 10. And then at this stage, you might just go ahead and divide. There is an important detail though here with inequalities. So I will divide by negative 4. That's true. Except when I do that, the inequality symbol flips. And that's only because I'm dividing by a negative. It's not the division that matters, it's the division by a negative. So I would need to now say actually that n is greater than the reduction of this 10 over negative 4, which is negative 5 halves. So this actually would be the solution. It would be completely wrong to say n is less than negative 5 halves. That would be totally wrong. Just to explain why for a moment, imagine we had a true statement, like 4 is less than 8. Okay, so this is true right now. Then imagine that I came through and I just divided everything by negative 2. Okay? I just came through and I said, you know what, let's divide everybody by negative 2. Is it still true that negative 2, right, the result here, is less than negative 4? Is this still true? This is now false. Negative 2 is actually greater than negative 4. So to keep the trueness, we need to flip. And now this is true again. So whenever you're dividing or multiplying by a negative, actually, it's either division or multiply. Whenever you have a negative involved in division or multiply, in order to solve your inequality, you need to flip that inequality symbol. So I'll go ahead and leave my answer this way. If you wanted this in interval notation, we'd be saying all the n's strictly greater than negative 5 halves. So I can have negative 5 halves in parentheses because it's not inclusive. I'm not including the negative 5 halves, comma, approaching infinity, right? Everything greater than negative 5 halves. So this would be the interval notation way of saying that. Let's try one graphically. I'm hoping to kind of further explain what these inequalities are actually asking of us. So what I'm going to do actually is I'm going to treat the left-hand side. So we're looking for when this thing is greater than or equal to. So this symbol means not only greater than, but or equal to. It, leaves the possibility of equality there. So on the previous page, I said it's not true, just to make sure I have the same thing here. Right, I said it's not true that 1 is less than 1. And that's the case, right? 1 is not less than 1, 1 is 1. But it would, so this is false. I'll just write it that way. But it is true that 1 is less than or equal to 1. So this is true. Right? 1 is less than or equal to 1. It's also greater than or equal to 1. So the equal to, this little line down here means you can consider equality in your solution. Okay, so for the purposes of this problem, actually I'm going to graph this piece in red, and then I'll graph this piece in blue. So what I mean by that is like I'll have y equals x minus 7 as one of my pieces, and then I'll have a y equals negative 3x plus 1 as the other piece. And we're doing this graphically. So to graph those, well, I'll graph this red one first. You can use the slope-intercept form. So the y-intercept is sitting right here at 1. And then from there you can use the slope. So down 3, 1, 2, 3, and over 1. Right? So this line in red would be the piece on the left. And then in blue, we have a negative 7 as our y-intercept. And then in this case, we have a 1 as our slope. So from that negative 7, I'll go up 1 and over 1, up 1 over 1, and so on. So I will draw this line. So let's consider what the original question is asking of us. And I'm going to try to just speak through this in normal terms. So when is red bigger than or equal to blue? So when is red above or on top of blue? Right, that's what this symbol means. So when is red on top of or above blue? That's what this question is. So looking at the picture, when is the red one above the blue one? Right, because I'm asking when is it above, because this is a greater than symbol. So you can see all throughout this region, right, all throughout this region, we have that this red line is literally above the blue line. On the right side of the intersection, it switches, right? Now the blue is above the red. In this situation, we're wondering when the red is greater than or on top of the blue. So all the x's, right? We're looking for x's. So I would say, for the solution actually, I would say that x needs to be less than or equal to, it looks like this is crossing right here at 2. So this would just be our kind of regular way of saying it as an inequality. And then if you wanted, you could say this as an interval. So less than or equal to 2 would mean we're approaching negative infinity and then kind of rising up to 2, including 2. So square bracket. Okay. I'm actually skipping a bit to page 54. Okay, so this is actually our first compound inequality, meaning there are at least 2 inequality symbols kind of in series there. So what this means, if you have A less than B less than C, and this would be true for less than or equal to, then this is what we call a conjunction. So what I mean by that is it would be equivalent to say A less than B and B less than C. So whenever they're written in this compound way, it's really an and case. So this is completely equivalent to negative 12 less than 3x minus 6 and 3x minus 6 less than 0. So this is the same interpretation. What I'm now going to do is solve, and then we're going to need to think about this word and. So I'll go ahead and add 6, add 6. I'll go ahead and add 6 and add 6. So I'm kind of solving these in parallel. So negative 6 less than 3x, and I'm just copying down that word because really this whole thing is our problem. And then I have 3x less than 6. So continue to solve. So divide by 3 here, divide by 3 here. That's a positive 3. So there's no need to flip the inequality symbol. I just still have negative 2 less than x and x less than 2. So we're tasked with solving and graphing. Okay. So the solution, what I'm going to do is actually first independently graph both of these pieces. So this piece would be, well, if this is 0, this is negative 2, all x is greater than negative 2. So I'd say everything to the right. Over here on this piece, if this is 2, this is 0, then everything, so by the way, this is an open dot. I don't know if I explained that at all. This is an open dot. Why is it open? Because these don't include. So we're not including actually negative 2. We're going right up to negative 2 and then everything above. And then this is x is less than 2. The and means we need to figure out what numbers are in both, if any. So the true graph, the true solution to this compound inequality is not this kind of tethered to this, it's the combination, the and. So what numbers are both greater than negative 2 and less than 2? So what numbers do that? So we would be going from negative 2, not including, and then all the way up to 2, and not including 2. This would be the graph of the solution. And to write that in interval notation would be the solve part, actually. So I would write negative 2, comma, 2. That's interval notation. That's not a point. So let's see a disjunction. This one has been a conjunction. So conjunction always results from this compound inequality. And it means we're looking for the and, meaning what numbers are in this set and in this set, and those are the numbers that go into our solution. For a disjunction, let's go over to page 56. So this will actually be the last one I do. And yeah, as I said, there is homework, but these two sections from chapter 2 won't appear on any exam nor any quiz, but yes, you do have homework on it. So for a disjunction, it's or is the word, right? These numbers or those numbers solve this type of inequality. So what I'm going to do is isolate x in both. So add 2, add 2, add 5, add 5. So this would now change to 6x greater than 6. Or 3x less than 6. Okay, continue to solve. Divide by 6 in this case, divide by 3 in this case. Those are both positive numbers, so neither of these needs to have their inequality symbol flipped. So x would still just be greater than 1, or x would be less than 2. So now in our solution, we're going to write all the numbers that are either greater than 1 or less than 2. So for this one, if this is 1, then greater than 1 would look like this. We'd have this open dot and then everything to the right of 1. For 2, we have again an open dot. If this were, let me just do this up here. If this were equal to or equal to, I would have a closed dot. Okay? But it is not including, and this is saying x strictly less than 2, so I'd have all the numbers to the left of 2. So what numbers does this set or this set include? It includes every number. So I would draw essentially this kind of double-sided arrow, just extending in both directions, because every number is either greater than 1 or less than 2, right? Just pick any number out of the air. 6. 6 is greater than 1, so it checks this box. It's not less than 2, but the requirement is just or. It doesn't have to be and, it doesn't have to be both, it just has to be either or. So 6 satisfies this one, so 6 is in our solution over here. What about negative 10? Negative 10 is not greater than 1, but it is less than 2. So for that reason, it satisfies this piece, and for that reason, it's in our graph way down here at negative 10 somewhere, right? This arrow is going to get there. So every number solves this one. So I would have negative infinity. Infinity, that'd be another way of saying this in integral notation. All right, bye-bye. Hello, almost forgot about 2.7. So let me skip over actually to page 58 and talk about an absolute value equation. So on the previous page, it'll spell out kind of how you go about these. So in a case where you have the absolute value of something equals a positive number, then you'll set up these two equations and you'll solve those independently. If you have that an absolute value equals a negative number, then there's just no solution. So in this case, we have the absolute value of 2x minus 5 equals 15. So just to conceptualize this, if 2x minus 5 is 15, then absolute value of 15 would be 15. So if I make 2x minus 5 equal to 15, that would be one way of getting a solution. But also, if you have the absolute value of negative 15, that would also equal 15. So another way of solving this would be to take 2x minus 5 and set it equal to negative 15. And solve both of these. So I'll add 5, add 5. So this one, we have 2x equals 20. And this one, we have 2x equals negative 10. And then divide by 2 in each case. So we get two answers actually. We have x equals 10 and x equals negative 5 as solutions, and you can check those, plug those in, take the absolute value. We should get 15. Down here at the bottom of the page, example 3. So here we have two absolute values, so an absolute value equal to another one. So what we need to do is solve this way, where x is this thing here, right, capital X, is this thing here on the left side, and capital Y is this thing here inside the other absolute value. So our solutions will come from 4x minus 3 equals 3x plus 5. That's just setting x equal to y. Or they'll come from setting 4x minus 3 equal to negative 3x plus 5. Right, that's this piece here, minus y, x equals minus y. So I'll solve both of these. So add 3, and maybe I'll subtract 3x here simultaneously. So x would equal 8 on that side. Over here, I'm distributing this negative. So I'll have 4x minus 3 equals negative 3x minus 5. Maybe I'll add 3 over, and then I'll add 3x over. So we have 7x equals negative 2, and then divide by 7. So this would be our other solution here. We have x equals negative 2/7. One more. Here's kind of where we're putting both pieces together. Here's an absolute value, and now it's not an equation, it's an inequality. I'll refer up to this piece of information up here to solve these types. So I'm first going to kind of figure out which brand this is. Okay, so we have an absolute value of something is less than a positive number. That would be this one right here. All right, absolute value of a thing is less than a positive number, right? We're assuming p is a positive number. So I'll look to part B here for the purposes of solving this inequality. What it says is that this absolute value inequality is completely the same as this compound inequality. So instead of just 13 like I have here, I'll have negative 13 less than 8x plus 5 less than 13, right? That's, I just did this part of, right? Something you can do is actually just leave it as is. So minus 5, minus 5. So you don't actually have to separate this. So negative 18 less than 8x less than 13 minus 5, 8. And then divide by 8. You can just kind of leave this written all in one line. So negative 9 halves is less than x, less than 1. So you can write this in interval notation as negative 9 halves, comma, 1, parentheses on both because they're non-inclusive. And then the graph would look, well, here's 1. Maybe I'll just call negative 9 halves over here. We'd have open, open, and everything in between there. So that would be the graph and the interval notation of the solution. All right. Bye-bye.